All right, so moving on from here, if we kind of think about the reactions we've seen so far, we've seen a lot of, we have some reactants come together, they make some products, and that's it. They just go one-way street. So, for instance, we have a hydrocarbon, some carbons of hydrogen like propane, methane, some C, some H's. They react with some oxygen, and we make, CO2 and H2O. See some flame and all that jazz. Or we could see two solutions coming together to make a precipitate. So we mix some stuff together, we get a solid, we can filter out. But up at this point, we haven't seen something like that precipitate break back down into its reactants and redissolve. Or we haven't seen that flame disappear. I mean, you wouldn't be able to see the gas it turns back into, but you get what I'm saying. So up to this point, we've just kind of seen chemical reactions that only go one way and not back the other. But if you checked out the simulation that we kind of looked at after the test last time, this is a kind of a precursor to maybe not all reactions have to go just one way. Maybe if we kind of ignore like going one way and then think about going the other, it's not so different. It's just some chemical making some change to something else. So it's a little bit harder to think about because we haven't seen some stuff in the lab with this kind of thing, at least not very visually. But chemical reactions that can go either way, or otherwise we call them that are reversible, are going on all around us at all the time. For instance, rechargeable batteries happen because of reversible reactions. So I have a chemical or a couple chemicals in a battery that do some reactions. They give you some energy and to power your device, and then we plug it in. We basically reverse that reaction. We get our reactants back so that they can react again and give out our energy again and power your device. Now, if you also think about something like a Coke bottle, we have some CO2 in there. And if we kind of approximate our solution of Coke as water-based, it's mostly water, and then it's got other sugar and caffeine stuff in there. When that CO2 is in there and dissolved in the liquid, we actually make carbonic acid. So if you ever noticed your pop go flat, if you've left it out for a while, your CO2 is leaving, and you have a little less acid in there. So maybe it doesn't have that kind of like, that kind of acidy, that sour taste sort of. It's just all sweet. So we have some carbon dioxide that gets dissolved in the water, and you can kind of get this acid. But as I kind of talked about, we can have this go the other way. The carbonic acid can kind of decompose back into some carbon dioxide and some water. So if you have an open bottle of pop, then that CO2 can just leave. So before we open the bottle, it's all pressure in there and it stays there. So we have kind of a mixture of both the CO2 maybe above in the space in your bottle, and you have some carbonic acid still in the liquid, which gives it that different kind of taste. So cool stuff. But this doesn't just happen in Coke bottles. We also see this kind of reversible reaction in the oceans, where we have carbon dioxide in the atmosphere dissolving in the ocean water. So kind of to bring this to current events, there's kind of this big thing about climate change where we have too much CO2 in our atmosphere, and that's causing kind of a myriad of problems. And one of them is something called ocean acidification. So we have some CO2 in the atmosphere more than usual, so now it's moving to dissolve into the ocean, and it makes it more acidic. Now, the stuff that lives in the ocean, like fish and coral and that kind of stuff, is used to its environment, and it lives in a very specific place in the ocean based on things like temperature and acidity, and so they rely on how their environment is at a given moment. But if you then start to mess with that, like say make it more acidic, you can start to wipe out parts of the ecosystem. So this is bad.
Isn't that why some coral reefs are like being bleached and stuff?
Yeah, that can play a part in it. I think there's also research now going on about temperatures changing in waters. So, but that also, it kind of ties in indirectly. So we have the ocean acidification that can affect coral, but we also have kind of a warming effect that warms our oceans more, and that I think is also being researched. I don't know if they found conclusions on it, but those both kind of play a part. So it all kind of still ties back in the CO2 thing, but Yeah, and even the batteries thing has some world issue implications. So we use usually lithium ions for our rechargeable batteries, but as far as how we obtain that lithium and how we kind of handle it when we dispose of it, can be kind of touchy. So that's another thing where we are managing resources and kind of taking care of the earth, and so environmental message. And we will get into this more as we move into acids and bases, so we'll come back to this. But for now, keep this in mind, especially as we go into spring break, and maybe some of you go to Florida or something, and they're swimming in the ocean, and think about the little fishies and all the global problems. Because that's what you do on spring break, you just think about all the world's problems. So anyway, we're talking about reversible reactions. Now, what we're using kind of the simulation to show is once we have these molecules kind of going through the reaction, they're going back and forth, we see some interesting things. So for instance, you might notice that we don't have the same number of molecules on either side. We also have this weird kind of bump, this roller in the middle. So we can kind of think of this as an energy barrier. Now, this isn't a physical wall that actual molecules have to jump over, but we're kind of using this as a model to represent that, to kind of think about this. So this kind of brings up a question. If reactions can be reversed, at least to some extent, as far as we know, why don't they all just go back? Why don't we constantly just see things turning back into the reactants and then going back to their products all the time? Yeah. If you want to shoot something out.
The barrier is kind of like one side takes more energy to cross it, and the other side not as much.
Yeah. And in this case, we're looking at our energy as kind of temperature, the average kinetic energy of the molecules. So if we need to cross this barrier, we need to have a certain amount of energy to kind of jump over it. And then you can see there's also some other effects, like maybe how you bump into other molecules. If we were doing a reaction other than just, say, having one thing, like this molecule A turning into molecule B, then you might have to worry about how do I get those two molecules to collide in the right way to make a reaction or something like that. We won't get too far into that, but I just want you guys to be thinking about what it means to have a reaction reversed. So yeah, so we are kind of limited by the energy of our reactants and products. So to kind of also model this in real life, I'm going to pretend like this part of the table down here is our grade platform here. Our energy barrier is going to be this table right here. And then our final grade platform is going to be the floor. So we've kind of got our energy levels. And I am going to be a molecule of B. And now for once I can finally be tall. I feel like, okay, well I can't say for once because I've done this in the other classes, but it's nice being able to kind of be above for once. So right now I'm on that grade platform, I'm a molecule of B, and I need to move over to change to A. No, I won't. And actually, you know what, this isn't bad. All I have to do is take this little step up. I don't have to exert that much energy to get up past this barrier. And then to become a molecule of A, I'm just dropping down. In this case, gravity does the work for me, and it doesn't take any effort once I'm over that barrier. And then I'm here, now I'm a molecule of A. So how much would you give me, like cash-wise, to try and jump back up here? Like standing leave.
$5 Monopoly dollars.
$5 Monopoly dollars? Well, that's good because I have to take Monopoly dollars. Because that's not real money and I'm not allowed to take actual bribes.
You won't do it.
I'm not actually going to do it because I would probably just like testing it, like I would probably go backwards and then hit my head on this. And actually, I could use a chair.
Why are you looking at the fire extinguisher? No, you'll break it.
Yeah. I'm gonna borrow this. So yeah, this is the point that was brought up. We could use the chair, right?
Do we?
So now I'm not on the same energy level anymore. Now this is not so bad.
So what would the chair be then?
Good question. We will be investigating that further as we go into this unit. I just can't get over this. It's too nice.
We're gonna try it.
Weeks.
Can I be a volunteer to show my energy change?
Maybe another time. So just because in this kind of example we have a certain energy level that we're sitting at here, doesn't mean we can't do something to raise it up, to get it over that barrier easier. So if you have ever heard of something like a catalyst, that is something that changes how our barrier is. Like if you want to think of it as height-wise. But we will be able to do other things to our reactant molecules to lift them up to a different energy level to get them over. Now that's a little bit more complicated than we're going to cover today, but keep it in mind that just because we kind of set these reactants and products at these levels doesn't mean we can't do something a little to them to set them at a different level. Keep it in mind. So, kind of bring this back together. We've got this stuff going back and forth. This stuff is constantly moving too. We are constantly making molecules of B from A in this, what we call the forward direction. And we are also constantly making molecules of A from B. We call it the reverse direction. Now we call it the forward and reverse direction just kind of out of convention. We read from left to right. So we kind of say that this is our reactant side, B is our product side. We're going forward this way and reverse back this way. But if I were to pretend like I had seen this before and flip this too, there's not really a difference. It would still be forward going this way even if B were on that side. So we still call this our reactants and our products, even though products can still technically react and go back towards this way. Does that make sense? So it's just kind of a wording thing. Now, this stuff is moving. It's moving and grooving. We have a reaction going at all times in both directions. So we call this dynamic. We're constantly moving. We're not just taking a screenshot. However, despite this being constantly moving, we do have something that doesn't change, right? Or at least approximately. If we look at the numbers down here, they're very small, but if you saw this on the simulation when you did it on your surfaces, we keep around the same number once we hit a certain point. So when the molecules first come in the simulation, you kind of will see a surge of molecules going from B to A because it's a little bit easier, right? You can go over this bump a little bit easier, and then it's just an easy drop down. But to get back up towards B, just like when I did it with the desk, it would be a lot harder to go back the other way. It would still be possible. Now, like, maybe if I was more athletic, I could get a better jump if I was taller, or if I ate a really good breakfast and I was just ready to, maybe even if I had like some room to like get a running start, I still wouldn't bet on me. But it doesn't mean that other molecules they can't make it over, and they do. But probability-wise, we see this sort of shift where we have more molecules of A, and we hit a point where that stops changing. We see it's kind of like a teeter-totter where we sort of end up with one side with more molecules, and then it stops changing. So we could say that the concentration of our reactants and our products have stopped changing, even though our reaction is constantly changing, back and forth. We have an exchange, a dynamic movement of our reactions. When we talk about concentrations for this stuff, we're going to put brackets around our reactants and products. So if we had multiple, each one would have its own set of square brackets. We call that the concentration of whatever is inside the brackets. Now you wouldn't do this on your actual reactions equations up here, but we're going to use this here in a second, and it's already up here, so I'm just kind of demonstrating it here. So this means the concentration of A. In particular, we're using molarity. So this would be the molar concentration of A and the molar concentration of B. These stay constant even though we have kind of reached this equally paced exchange from the forward direction and the reverse direction. In other words, we have reached equilibrium. So even though the reaction is constantly going, we have the concentrations staying the way they are. And since they stay the way they are, we can relate them mathematically. Again, since they're changing, this will equal a constant ratio. So we're using this constant, KEQ, or the equilibrium constant. And we're going to relate our products to our reactants. We want our products on top and our reactants on bottom. And then we can relate these concentrations to get a number. Now, since this is a ratio, yes?
You're basing this off of that, right?
Yes. Yeah.
Is A the reactant because more flowing?
A is the reactant because of the way we write it. So in the equation up here, CO2 and H2O are our reactants.
Yes.
But in a, say, combustion reaction, they would be products most of the time, the way it's written. So since this is reversible, you can switch this around and it's equally valid. We just call it the reactants because of the side it's on.
Okay.
So when you start working these out, the top will always be what's on the right side of your arrow. On the left side will be your reactants. Now, talking about arrows, you'll probably see something like this up here on the front, or what I've kind of drawn across here. But we can see other arrows too. So on the worksheet today, you might see an arrow like that. Kind of just back and forth. Or like that. Chemists tend to like this sort of double arrow where you have like just the one side. So conventionally, this is what you'll see a lot in textbooks and very technical papers. But in this class, I think as long as we can tell the reaction's going both ways, you're fine. Any questions so far? Okay, cool. So we can relate these two mathematically when we get a number. Now, since we're just dealing with a ratio, we don't really care about the units. So even though the brackets mean a concentration of molarity, that's where we get our number from, we're not going to include the little m's in there. It just kind of clutters things up, and depending on how your reaction is set up, how many products and reactants you have, it just, all your units get nasty. And so this will be one of the few times where our constant, our KQ, is going to be a naked number. No units, no molarity, no nothing. So you get a number from this. But this is kind of a very simple reaction of this one thing becoming another and back and forth. So when we get into some actual reactions, like this one up here, we're going to have some rules we have to apply to how we write this. So I'm going to erase this. And then we'll use the carbonic acid example to kind of walk through this. So the way I have it written, what are my products? What product?
CO2.
Product? H2CO3. Since it's on the right side, we call it the product, even though our H2CO3 can still break down and reform the reactants in its own kind of reaction. So I want the concentration of that on top. Now I want the reactants on bottom. However, when it comes to writing these in, we have a couple rules. Like solids and liquids don't count. We want them in our equation up here because this will allow us to balance it correctly. But when we do our KEQ, they don't affect. Gases like CO2 and solutions like the H2CO3 kind of dissolved in water are fine. We can include them in here. But if we have just say water as a liquid, we don't want it down here. So our reactant would just be CO2. Now the reasoning behind that is a little complicated, but in essence, if you want to think of it like this, if we are worried about how the reaction is sort of proceeding, the liquids and solids do not have as much of an effect on how this equilibrium can be shifted. So just like how we kind of added a bunch of molecules in the very beginning, we could also add a whole bunch of molecules in right now. We could add a whole bunch to B. Now let's say we do that, and we add a bunch of molecules to side B. What's going to happen to our products and reactions? Where are those molecules going to go? Well, they're going to tilt back to A. Why? It's easier to get over there. So even though we add a whole bunch more onto the side B, it's going to tilt back over to side A, and we're going to make more reactant. So we can kind of use that value of the KQ to relate that. So no matter how much A we start with, or how much B we start with, or how much more we throw in, we can get this ratio to be the same for this reaction at those conditions. So you'll get a number here that kind of tells you your concentration of products to reactants. So if our products are on top, and we get a number, say like 5.0, do we have more products or more reactants? Products. What about now? Reactants. I kind of led you with that. That's okay. call this favoring. So if the KEQ is greater than 1, we say it favors the products. So we're tipping more towards this way. Otherwise, we will tip kind of back the other way. So I'm not going to write the other one out because it's just going to be kind of copying this, but the other way. So if you're less than 1, you're favoring the reactants and so on and so forth. So that's another thing we have to keep in mind when we kind of move on towards things like how we use this in the industry. Say you're making some product and you want to sell it, big bucks, you got this great new chemical, but if it's made with a reversible reaction and 90% of your stuff is going towards your reactants, not your products, you don't have much product to make money with. So if you want to shift that back over somehow, you need to do something to your system to change that equilibrium. So we will get into that more later on what you can do aside from just adding more molecules or something to kind of tip things around. But this will come in handy for how we tell where our products and reactants are in terms of concentration relative to each other. And this should be true, again, for the reaction that we write it for, as long as we are at the same conditions. Now, final thing is we have to watch out for the coefficients in our reaction. But I just mean the little numbers here. So for this reaction, it's simple. We just have 1s across the board. We use these as exponents. So for H2CO3, we have a 1 in front of it. So we take that concentration, or that value of concentration, to the first power. Same with CO2. So really these are the same number, but we would need to be more specific with a reaction, say, number 9 on the back of the worksheet for today. If we have coefficients like 2, 3, 5, 9, 27, hopefully it's not 27, that would be annoying to balance. But we will use them as exponents up here. Once we start plugging in numbers to this, like on the front side, you gotta be careful because it's real easy to forget these when you move on, especially if it's just like you have like one little 2 here, and then you go plug your numbers in, and you take this divided by this, and you forget to square it. Wrong answer. You gotta watch out for those. I'm going to shorten coefficients to co-op. So we're just talking about the numbers out in front. So we gotta use this as exponents. And that's basically our KEQ. This is how we relate our products and reactants in a reversible reaction that reaches equilibrium. Any questions? Okay. So that's basically the basics. And so if you guys are all good on this stuff, the rest of the time is yours. I will kind of walk through and explain what's going on with the 2 assignments. So one of them is a columns writing. So 5 lines, edge to edge. I don't care if you skip lines or not, that's fine. If I need to write in comments, I can do it on the side and point arrows. So I would rather use, to kind of spend your area of your page using it as you need to. For the worksheet, on the front side, we have kind of a step-by-step process for setting up our KEQ equation with a reaction. So you're going to write the reaction equation. Remember that since the phases of matter help us determine whether we actually want our chemicals in the KEQ expression or not, make sure you have them on here. Otherwise, you're going to wind up with stuff in here that's going to mess up your math. It's going to be different. Remember that you don't need units on this. So leave off your M's in here and all that. And then you're basically just going to be plugging in numbers in here based on the concentrations of what we are dealing with. And then run it through and you'll get an answer, and that is our ratio, or that is the value of our equilibrium constant. Now on the back side, we don't have any numbers for these. We're just going to be plugging in, or setting up our equilibrium expression for a whole bunch of problems. And then just watch out for number 10. It is partially balanced, but not totally. So double check it and make sure you fix that, because that will change your exponents. Any final questions before I let you loose and let you just kind of work on stuff? Cool. This is all we have until class ends for spring break. So if you can get this stuff done, you will not have any homework before coming back. You can easily get this done in the time we have left.